Hi, everyone, and welcome to episode 612 of People Behind the Science. I'm your host, Dr. Marie McNeely, and today we are going to be chatting with our guest, Dr. Ed Belbruno. Listeners, if you want to continue meeting more exceptional scientists through our show, you can follow us on Twitter at PBT Science, and I'm at Ph.D. Marie. Now today, Ed is going to be sharing some wonderful stories and insights, so get ready to meet another one of our brilliant people behind the science.
Every day, discoveries are made that will change our understanding of the world around us. Dr. Marie McNeely is here to bring you the brilliant minds who are making these discoveries so they can share their incredible stories and take you on an amazing journey. Welcome to People Behind the Science.
Hello, everyone, and welcome to People Behind the Science. Today, I am thrilled to be speaking with our guest scientist, Dr. Ed Belbruno. So, Ed, welcome to our show today. How are you?
I'm doing great. Thanks for having me on. I really appreciate it.
Well, thank you for being with us today, and I'm looking forward to chatting more about you, your life, and your science. So let's dive right in, and I'll start by telling our listeners a little bit more about you and your background. So listeners, Ed is a professional artist specializing in abstract expressionist paintings. He's a clinical professor of mathematics at Yeshiva University, a visiting research associate in the Astrophysics Department at Princeton University, and president and founder of the company Innovative Orbital Design. Ed received his associate degree from Mitchell College and his bachelor's and Ph.D. degrees in mathematics from New York University. He then worked as a faculty member at Boston University for about 5 years before accepting a position as a trajectory analyst at NASA's Jet Propulsion Laboratory, or JPL. After leaving JPL, Ed held positions at Pomona College and the Geometry Center at the University of Minnesota. And throughout his career, he has received a number of awards and honors, including Germany's Humboldt Research Award in Mathematics. He also received the Laurels Award from Aviation Week Space and Technology magazine. He was named one of the top 10 most influential space thinkers by New Scientist, and he was the subject of a feature documentary movie entitled Painting the Way to the Moon. Now, Ed, we're excited to get to know you today, both as a scientist, but also as a person in general. So can you tell us, what do you like to do when you're not thinking deeply about math and science?
When I'm not thinking about math and science, I do my other career, which is I'm a painter, and I did my first serious oil painting at 7 years old with no instruction. And that painting was a picture of Saturn in the sky from the moon of Titan. And it came out so good that I had an art show recently in New York, and they actually used it to advertise the art show.
That's amazing. So I have to ask, I know you have this successful career as an artist and also this very separate successful career as a scientist. How do you do both?
Well, I don't sleep very much.
That always helps.
No, but I'm very focused at it. Naturally, when you first get started at either of these two things, it's hard to balance because you need to focus all of your attention just to learn one of them because you're still learning the ropes, so to speak. But at this particular point in my life, I really mastered a particular style in art that I really like, and I'm efficient with it. So I can spend relatively less time. And similarly with the science, I don't need to spend those exhaustive hours because I have a lot of the basis down that I really need. So the trick for me is being very focused. I can do a lot in a short amount of time, and that allows me to do both.
That's phenomenal. So what is it maybe specifically about oil painting that really captivated you?
I don't really know, actually. It was sort of in my blood. I grew up way back in the dark ages in the 60s, and my mom was shopping in the town I grew up, New London, Connecticut. And while she was shopping, I would just go to the toy stores and look around for toys, being a young kid, like 5 or 6 years old. And I just gravitated to the paints, and I sort of instinctively knew what to get. The typical supplies one gets in oil paintings that you go to art school for, but I sort of knew it intuitively, so I bought the supplies, and I was just attracted to it. I really can't give any reason what did that. However, I was definitely totally into rockets and space travel because at that time in the 60s, it was the whole thing about the Apollo or going to the moon, and the public was just saturated with this. So as a young kid, I was absolutely fascinated by it. And from the day I can remember thinking I was interested in space. So naturally, I drew one painting was a satellite I saw from the cover of a magazine. Another was this picture of Saturn in the sky from the ground of Titan, which I saw from a book of a famous artist called Chesley Bonestell. And I was instinctively did it. No one told me to do it. In fact, my mother didn't even know how to react to it. She was not brought up in her own environment to recognize this, and she just let me do it.
Oh, that is phenomenal. And you mentioned you had this early interest in rockets and space travel. And I know you are doing considerably more complicated work these days, as I'm sure than you were as a child, kind of starting to investigate this area. So how do you kind of break it down and describe your scientific work to someone who might not be very familiar with your field or familiar with this area of astrophysics?
So I ended up, without even wanting to do this, because I went to college reluctantly, actually, and was drawn to math, not because I liked it so much, because it was really easy for me. So I ended up getting a Ph.D. in math, and I never really intended to ever want to even think of doing anything like that. And the math I was interested in kept my love for science, space going, because I remember when I got into math and actually decided to go to graduate school in it, I said, well, let me at least keep this focused on space. So there's a particular kind of math which deals with space, and it's called celestial mechanics. It's the way things move in outer space. So if you ever thought of a way spaceships might move, like if you have a spaceship going in orbit around the Earth, and then the spaceship is targeted to go to the moon, for example, how does that happen? What does it look like? You have the moon going around the Earth in a circle. You're standing on the Earth, and the moon's going around you. That's really what happens. And it's going at very, very roughly a mile a second. It takes 1 month for the moon to go around us. So basically, if you're sending a spaceship to the moon, how would you ever get there? I mean, how do you do this? So basically, the spaceship has got to blast off from orbit around the Earth somehow, and it goes away from the Earth. But as it goes away from the Earth, it just doesn't go in a straight line, because after all, the moon is moving, and it takes about 3 to 5 days to even reach the moon. So you have to think about this problem in relative terms. You're sort of arcing away from the Earth in a big arc, but you have to be very mindful of where the moon is, because if you actually arc out and go to the distance the moon is about the Earth, which is about 250,000 miles, it takes, like I said, 3 to 5 days to get there. You have to make sure when you arc out to that distance, the moon is actually there. So you have to make a rendezvous problem. The moon's going around, you're going out, and they have to meet up at the same place. So that's an example of how celestial mechanics works. It doesn't have to work just for spaceships going to the moon. It can work for asteroids moving around the sun, the Earth moving around the sun. It has to do with the way moons move around Jupiter or Saturn. It's the way objects move in outer space. Now, the kind of math that I was trained in was sort of that, but it was a lot more complicated. Basically, if you move in outer space and you do it with a lot of oomph, a lot of push, a lot of speed, you could almost see yourself moving in a straight line. So if you're like out there floating around in space, let's do a baseball. So you throw that baseball. Now, if you throw it incredibly fast, it's pretty much going to go in a straight line. And the motion is pretty predictable. It just looks like a straight line. And you could follow it as far forward as you want. It'll just keep going unless it runs into something, like the moon. Mm-hmm. However, the kind of motions that I deal with are called chaos motions. We all know what chaos is. Chaos has to do with very random-like motions. So the kind of joke that I like to tell is if you're going to a party on a Friday night and you've had a little bit too much to drink, if you're trying to walk, that's called chaos. Or if it's a fall day and leaves are falling off of a tree and it's a lot of wind blowing out there, the leaves don't go flying to the ground like cannonballs. They drift and dart all over in a very, very complicated way. That's chaos. So chaos is a very delicate, complicated motion. So what I studied, to sum it up, it's called chaos motions in space. So basically, it's how does an object move in space where the motion is extremely delicate? And obviously, if you're sending something to the moon and you gradually sneak up on the moon's gravity is pulling you in. But on the other hand, if you do it really slowly or gradually, the Earth's gravity is pulling you away. So there's this tug and push between the Earth and the moon, and an object that's going towards the moon very slowly is going to feel this forward, backward, and the motion can look very delicate. So that's called a chaotic motion, and that's the kind of math that I work. It's chaos motion in space, and as my story is going to be described, I've had a tremendous amount of success with that in finding new ways for spaceships to go to the moon and other destinations for very low cost. Low fuel, that is. However, in recent years, I've applied these same techniques to astronomy and astrophysics, where you can talk about motions of how the moon even got created. That actually turns out to be a chaos problem. I've applied these kinds of ideas to the Big Bang that created our universe, we think. Some big event happened 14 billion years ago where there's somehow some huge event happened where our universe got created. And you can apply these techniques to that problem, which is studied in the field is called cosmology, the study of the origin of the universe. And now I'm studying motions like this, but they occur in our galaxy. It's called galactic dynamics. So these are all astrophysics kinds of problems. But the main area that I've worked in over the years, I think the most, is these chaos motions for our solar system, and in particular for spaceships, which has a big application for NASA and other big space agencies around the planet, like the European Space Agency. I've done a lot with them. Or the Japanese space program. I've done a lot with them. And that's sort of how it works.
Well, Ed, this is really cool. And I look forward to diving into more of the stories as we go through our conversation today. And I think as a scientist, motivation and inspiration are pretty key to being successful. So do you have a particular quote or a saying or even just a force that keeps you motivated and inspired?
I was born that way. In fact, I was born in a military base in Heidelberg, Germany. And my father, who's now long deceased, told me that when I was born, I came out laughing. So I was born this way, just very optimistic, inspired, happy kind of person. I really am. I mean, it takes a lot for me to get down. I'm usually very excited about things, and the motivation seems to naturally just be there.
Oh, well, I think that's amazing. I love the idea of coming into the world laughing because I think that sense of humor is really important. And I think as you go through science, you meet some phenomenal people who might inspire you or kind of help you at different key stages of your career. So, Ed, for you, when you think back, do you have any role models or mentors or people that just really had a big impact on you?
Well, even in my earlier days when we didn't have the internet, there was things like Life magazine and other big periodicals. So we're all inundated with the same information, so you see the same kind of people. There was one fellow, I don't think many people heard of him, Victor Zebehay. And I remember I was probably a 10-year-old kid and I was reading Life magazine. At the time, that was the equivalent to the internet today. And if you were anything and anybody, you were in that. And I remember reading about him, and this was a period when they were going to be sending people to the moon. And he was one of the guys who designed the trajectories, the routes to get that spacecraft to the moon for the United States, the Apollo. And he was called the three-body expert. That means the three bodies of the Earth, Moon, spacecraft. How do these three things move, all moving with respect to each other? And I described that to you before, with going to the moon, with the Earth, gravity pulling you one way and the moon pulling the other. That's called the three-body problem. And I first read about that when I was like 10 years old, and Life magazine was describing this by this particular guy, Victor Zebehay, who was called the three-body expert. That absolutely fascinated me. And when I went off to get my Ph.D., I got to meet him, and I told him that story of how I saw him. And he goes, I remember that article. So he was somebody who inspired me. Actually, you hear the name all the time, but Albert Einstein, of course. Mm-hmm. I was never really interested in what he did, that kind of physics relativity. But his name obviously was big. And I remember as a young kid, really young, like 5 years old, he was still alive. And I remember he gave some talk at the Hollywood Bowl and was on television. All I can remember as I'm thinking about it this moment is my mother said, Edward, you have to look at the TV. This is a very smart man. And that's all I remember. But Victor Zebehay, I would say, played a big role. And also, I grew up in New London, Connecticut, which is on Long Island Sound. It's where the United States submarine base is located and the Coast Guard Academy. So I was steeped in living by the water, the beaches, going on fishing boats, sailboats, all of that. I was really into that. So I was really into oceanography. Actually, that was my first science love beyond space. And Jacques Cousteau, he was very inspiring for me. I saw him on TV all the time, and I remember being highly inspired by him. In fact, when I was 14 years old, we actually did an underwater experiment with an aquarium and using a special membrane which allowed the air to come out of water and CO2 to go from inside the aquarium into the water. We kept a mouse alive underwater for about a month. And we used to dive down every day to see this. It got on the front page of the Hartford Courant newspaper, and I ended up getting offered a research grant from the National Science Foundation at 15 years old because of that.
Oh, wow.
And so my love was oceanography, really, and it seemed more realistic to me for a career, even though I wasn't really thinking about it at the time. But so anyhow, Jacques Cousteau was a huge influence. I was not exposed to many famous, inspiring people that one might if you grew up in a family that had maybe professors in it or people of that nature. I grew up with my mom. My parents were divorced, and my mom was not really into science. So I just saw people who inspired me from the popular media, and Cousteau, Einstein, and Victor Zebehay pop out. But as it turned out, Victor Zebehay made a huge impact on me because that's precisely the field I went into.
Oh, that is remarkable. And it sounds like already at a young age, you were out there exploring the world, kind of being really curious and starting your own experiments. So when did you decide that science was going to be a career for you? And maybe how did you get from that curious kid to the scientist that you became?
It's actually a fascinating story. I went to New London High School in the late 60s, and I was really not into studying. I was into the scene at the time, which was very heavy into rock and roll and all of that. And the music scene then was just dwarf what we have today. I mean, Led Zeppelin, the Beatles, Rolling Stones, Aretha Franklin, on and on and on. Just incredible amount of music we had then, Janis Joplin. So we were just transfixed to the whole music scene. So I spent a lot of time just going from concert to concert and having a lot of fun with that. And I was not into studying. I got into a local junior college that my mother happened to work in the bookstore, Mitchell College. They were a 2-year college. And at that time, we had these 2-year colleges, which no longer exist now. We have community colleges instead, which are watered-down versions of those. These 2-year colleges were outstanding. They were for people who really weren't serious enough to want to go to a 4-year major college. They go to these. But these had the same programs as the regular universities, and you had automatic transfer plans. So when I went to Mitchell College, I had an automatic transfer plan to go to NYU or Cornell, and I went to NYU. So they were outstanding. And while I was at Mitchell College, the first semester there, I was still in party mode, and I didn't do very well that first semester. They almost weren't going to admit me because of my reputation.
Oh, no.
Even though my mother worked there and it was a junior college. But they did let me in. And the first semester was a disaster. And I ended up at the hospital for just too much partying, I guess. So what happened was when I got back there, I was so scared by that the next semester, the spring semester of 1970, I guess it would have been, I worked my butt off. I worked so hard that I said, look, I cannot let this happen again. I really have to take this serious now because I saw that party days are over. So I ended up getting the highest scores I think they ever had at Mitchell College in math. And I went from a lousy math student to the best they ever had. I was doing exams that would normally take an hour and a half, 2 hours long, doing them in 20 minutes. And I just excelled in the math. I did so well that it shocked me and everyone else there. And when I finally finished Mitchell College, a philanthropist in New London, Connecticut, came forward and offered to fund me for whatever funding I needed to go on to college at all levels. So I had a blank card for unlimited funding to go to NYU for however long I was there, and for everything, not just the college, but the living and everything. So I went off to NYU, and because I did so well in the math, I also had this love in chemistry. And that was my second big love, and I was a chem major. But I kept doing the math because it was easy. In particular, I was taking some astrophysics classes as undergraduate, some simple astronomy classes. And it turned out that I stuck with the math because it was easier for me. And also I reasoned at my senior year of college that I'll take chemistry as a minor, I'll stick with the math because math at least gives me a chance to get into the field of space by doing the celestial mechanics I mentioned. And I figured maybe I can pull that off. So the following year, after I graduated NYU in New York City, of course, I went on to graduate school there. And I said to them, do you have anybody here who does celestial mechanics? And they said, well, we have the number one guy in the world, Jürgen Moser, who's a mathematician.
Oh, wow.
This German guy, and he's like the best in the 20th century, probably. And he offered to be my advisor. And I was able to bring the space together with the math. And because I was good at the math, it gave me a backdoor into the field of space, really. And when I got finished with that, I was on my own as a professor. And then actually I ended up working for NASA for a while.
Absolutely. And I love this idea that this quantitative interest and really these quantitative skills that you had seem to keep your options open and open a lot of doors for you along the way. And I think that's still very true today for people out there in science. Having those quantitative skills really gives you a competitive edge when you're looking at different career opportunities.
That was also another motivation I had, believe it or not. When I went to NYU, I went there after I finished the first 2 years at Mitchell College. And my junior year is when I arrived at New York University. And I remember at that time, I was doing some very interesting artwork. And one of my friends at NYU saw it. And his father was a big art dealer in New York. And he was so taken by my art, he introduced me to his father. And his father was going to start dealing my art in Soho in a major way, actually.
Oh, wow.
And I got frightened of that because I knew nothing about the art industry. And he just said, yeah, just send us your work. We'll sell them. I mean, I had no agent. I knew nothing about how it operated. I said, I'm just going to give you my paintings.
Right.
So I said, I better get myself a field where I can keep my art going and at the same time be guaranteed of employment. And that way I can do both guaranteed employment and have an art career simultaneously. And that was another motivation for math because I knew that if you were good at mathematics, you could get a job doing anything. You could be an applied mathematician. You could work for a drug company. You could work for NASA. You could be an academician teaching. It goes on and on and on. And the short of it is, if you get a math training, you'll never have to worry about being unemployed again. So I used that on purpose to keep the art going. And at the beginning of this interview, when you were asking me about doing two careers, because I am a highly focused person, I'm able to really focus my time and do the art as I need to. And then when I'm done with it, I can go on to do the math as I have to do it to make my living. So as anybody in the arts will tell you, if you're an artist, everyone says, well, what's your real job? And the math for me has served that really well.
Oh, that is phenomenal. And I know, Ed, you have so many cool projects going on right now. So is there one in particular that you're maybe the most excited about that you want to go to in some more detail?
One of my interests is basically intriguing problems in astrophysics, which has a lot of math associated to it. I'm just drawn to those kind of problems. And one in particular, it's one of the most interesting problems and probably the most interesting problem in all of physics today. And it's called the issue of what is this stuff they call dark matter? I could crack a pun and say, what does it all matter? I won't go there because it's such a bad joke. But basically, this is the story of it. I'm sure the listeners out there will just be riveted by this if you don't know it already. So basically, if you look at our galaxy, like we live in our galaxy is a sea of stars. It looks like a big pinwheel and it rotates very slowly. And it's got like a bunch of arms, these arms coming out from the center. And the center of our galaxy is a black hole that has the equivalent mass of about 40 million suns. If you can imagine anything like that, I can't, but it's just dwarfs the imagination how big that is. That's the center of our galaxy. And then it has these spokes that come spiraling out. And on those spokes is concentrated stars. And our galaxy, here's a number I'll throw at you. It's got about 300 billion stars, if you can even remotely put your head around that. There's roughly 8 billion people on this planet. And you know how many people there are here if you travel around. So you can imagine 300 billion is many orders of magnitude more people on the Earth.
Oh, sure.
Those are stars, and our sun is just one of those. We're about 1/3 of the way out on one of those spiral arms from the black hole at the center. So we're not by any means even on the edge. We're sort of towards the start of it in the middle. And we're only one of 300 billion stars. Now, our star, the sun, has a bunch of planets going around it, 8 planets. And presumably all the other stars out there are planets too. If they do, the number of planets alone in our galaxy is in the trillions. So with that said, what astronomers did back and have done, astronomers like to count things. So they basically take their telescopes and they look at all the stars out there, spending years and years doing this. And they can figure out roughly how many stars there are, what kind of stars there are, how much they might weigh, what their mass is. Do they weigh 1 million times more than the Earth? How much do they weigh relative to the sun? Our sun basically weighs 1,000,000 times more than the Earth. So the sun is a gigantic thing. So what they do is they try to figure out how much our galaxy weighs, and you come up with some incredibly big number. It's to take the mass of our sun, which is 1,000,000 times bigger than the Earth, and then you add 12 zeros to that, and that's the mass of the galaxy.
Oh, wow.
It just dwarfs your imagination. It's a big thing.
Mm-hmm.
So what you end up with is you end up with a number. It's not really actually, something, it's not even important what the number is. You come up with a number for the mass of the galaxy by just counting all the stars and the black hole in the center, and you come up with a mass. So let's call that M for mass. This is the mass of our galaxy. And astronomers were happy with this. But then they found another way to figure out the mass of the galaxy. The other way you figure it out is the galaxy slowly rotates, and you know how big it is roughly. And based on its rotational speed and how big it is, you can also indirectly figure out how much does it have to weigh to rotate like that. And you come up with another number. I'll call it M2. Instead of M at the beginning, you have M2. That's easy enough. Everyone gets this. So basically, what you have to do is satisfy the equation. If your physics is correct, if you're like doing the correct physics and counting, you have to come up with the fact that M had better equal M2, right? If they don't, you're in big trouble. Something's not right.
Right.
Now, M is the actual mass of all the stars that you can see. And with modern computers and all that, there's like 300 billion of them, and that's the mass, M. Now, when you figure out M2, you come up with a different mass. Now, it turns out, this is actually shocking, the mass of M2 is 98% of the mass of the galaxy, and the mass of M is only 2% of it. So basically, 98% of the mass of our galaxy, we cannot see it. And people figure, well, maybe it's because we just can't see it. Our telescopes aren't good enough. Or maybe there's things out there that are too little to see. They've ruled everything out. And at this point in physics, they know that it's something completely mysterious. They don't know what it is. And they call it dark matter. So dark matter, it's called the missing matter problem. What is dark matter? Nobody knows. And it turns out that all galaxies have it. All galaxies that can see the way they move in outer space, they also have dark matter. So currently, it's probably the number one problem in physics today is like, what the heck is dark matter? So it's a problem that I got drawn into, not because of dark matter per se. It's something I need to work with. But there's a problem that I'm working on with my collaborator at NASA. Now, he's the chief scientist of NASA. He's the number one scientist of NASA at NASA headquarters in Washington. His name is James Green. And he got me interested in this problem. And actually, I was interested in it before I met him, but he renewed my interest in it, I should say. And basically, NASA sent a spaceship away from the Earth back in 1973. So I'm now shifting gears. I'm talking about spaceships, no more dark matter. Mm-hmm. They sent a spaceship away from the Earth in 1973. It was called a Pioneer 10. And basically, it's been moving ever since. And it's now really, really far from the Earth. It's basically 120 times the distance the Earth is to the sun. So it's way beyond all of our planets, way the heck out there. And here's the problem. They saw in the early 90s that the Pioneer spacecraft is not where it's supposed to be. It shifted. So they found there was a mysterious force acting on it. And they didn't know what the force was. It's called the Pioneer anomaly. What is causing this force? This unknown force is called the Pioneer anomaly. And I had an idea back in 2007 that it was due somehow to dark matter, although I had no clue why that was the case, because I didn't understand anything about dark matter then. 2012, some scientists at JPL, engineers, said, well, probably what it is due to some mechanical device on the spacecraft is not working right, and it's slowly leaking, and it's making a little tiny force, which is pushing this off course. However, Jim Green, Dr. Green, got me interested in looking a little bit at what dark matter is. And as I did, I sharpened up this idea I had back in 2005 or so, that maybe dark matter has something to do with where the Pioneer is. So I did some calculations and wrote a rough draft of this result. And the result is that dark matter makes a force, a little tiny force, and the force is roughly equivalent to the Pioneer anomaly. So our paper has to do with using dark matter to try to understand the Pioneer anomaly. And our current result is that the Pioneer anomaly is partially caused by this and not entirely by the mechanism that the NASA folks thought were the case. So this is the current problem I'm working on. It's gone through several versions. I'm now on version number 5. And one of these days it'll converge to something good.
Oh, wow. Well, Ed, this is a fascinating area of study. And I know there are a lot of different challenges in the work that you do, specifically related to dark matter and some of these trajectories that you're working on. And you've overcome so many challenges in your career, knowing myself a little bit about your story. So do you have a particular story about a challenge or a failure that you've faced that you can tell me and our listeners about, maybe give some insight into how you worked through it?
So when I was very young, 5 or 6 or 7, there was a publication out. Now, I actually found it in the attic of my mother's house, believe it or not. She's long passed away, but I found it a couple of years ago. And it has a picture of an astronaut in the article, and it's talking about astronauts. And at the time, when I was up in the attic talking to my mom, I asked her what an astronaut was, and she goes, "Don't ask because you're not smart enough to become one."
Oh, no.
Right, I was told that at a very young age. And of course, it made a big impact because, after all, I still remember it.
Mm-hmm.
Like I say, they should make a license for parents. That was not a good thing to tell a kid.
Right.
However, I have to say, her telling that to me was a huge positive thing, because I was convinced when I heard that at, say, 7 years old, that on some level I wasn't smart. But deep down, I knew I was. I had this deep knowing that I was incredibly smart, actually. But on the surface, I was told I wasn't. So it was something that I challenged myself with proving I really was. And this motivated me, to be honest, to get a Ph.D. in math. Now, when I got a Ph.D. in math, that helped me resolve that. It helped me feel that I was, yeah, you are smart. You did this. It didn't really sink in with that, believe it or not. And it only happened a few years later when I was working with NASA at the Jet Propulsion Laboratory in Pasadena, California. This is the organization that launches those famous missions to Mars you always read about. And I was hired there in 1985 to work for them, designing trajectories to get spaceships to Jupiter, believe it or not. So it goes back to Victor Zebehay I read about when I was like 12 years old. I'm literally doing that job now. In fact, he worked there for a little bit. So during that time, I came up with my own theory of how to get things to the moon using chaos. What does this mean? It means you go to the moon slower, and then you get this chaotic motion I described earlier, the push and pull of the Earth moon. And if you go slow enough, the chaos increases. It takes longer to get there, but you end up saving a lot of fuel because you don't have to worry about using fuel to slow down. The moon just naturally just pulls you in. And this was an idea I came up with when I worked at the Jet Propulsion Lab. And everyone thought it was a crazy idea. In fact, I was almost lost my job even thinking about it. They didn't want to worry about this idea because I was using chaos, and they didn't want to deal with that term because up to that point, chaos was not ever used in space travel, ever. And because JPL does these multi-billion-dollar missions to like Jupiter and the Mars and all this, they didn't want to be known as an organization dabbling in chaos theory. So my job was on the line. And what happened was, around that time, I had the incredible opportunity to literally rescue an errant Japanese robotic lunar probe that was wandering around Earth's orbit with there's barely any fuel in it whatsoever. And its intention was to get it to the moon. And by using my chaos theory of low energy, low fuel ways to the moon, using chaos, they asked me to apply it to their mission. And I found a brand new route to the moon for it. This was in 1990. And in 1991, they actually used it. And it got to the moon in 1991 in October, the first spacecraft in history to use this chaotic route to the moon. And as I tell people, it saved their mission and it saved my career. And when that happened, I then knew I was smart enough.
Oh, wow. Well, I think this persistent voice of doubt is something that so many people struggle with, and it is a tough hurdle to overcome. But I'm so glad to hear you didn't give up, and this lunar probe rescue ended up being an amazing success. And Ed, we love talking about success on the show. So do you have another success story that you wanted to share with all of us?
Another favorite one, well, gee, there's a whole bunch. This one with the lunar was very key, though, because this was very traumatic to be working at this NASA center, having them not believe my theory, almost firing me after I quit a professorship to go there. And then very last minute rescuing the spacecraft. It was very traumatic and incredibly exciting. I would never want to do that again. But another one, which was a very exciting success, was working with a fellow at Princeton University, where I have a position. It's my research position. I'm a regular math professor at a university called Yeshiva University in Manhattan. However, I have a research position at Princeton University. I've had that for almost 20 years. And it's in the Astrophysics Department, actually. And one of the professors there got me interested in the astronomy problem. It was how the moon was created, literally. So you look up at the sky, you see the moon. Where the heck did that come from? And this guy had an idea that, the current theory where that comes from actually came out of the Apollo era. When the astronauts went to the moon, they discovered that the material the moon was made of is identical with the material under our feet on the Earth's mantle. So it looks like the moon actually came from the Earth. How could that ever happen? So it gave rise to, in the middle 70s, what they call the big splat theory. And what that means is something large slammed into the Earth, and the explosion was enormous, and a bunch of lava got flown into space from the Earth. In other words, a piece of the Earth came out, and it coalesced into a small object, the moon. So it's called the big splat theory, that some object hit the Earth to form the moon. And that was a very well-known theory that came out of the Apollo missions to the moon. But no one ever said where the object ever come from that hit Earth. Now, the object is about the size of Mars, actually, roughly a third the size of the Earth, so it was huge. So where'd that come from? And no one ever explained that. So this particular professor at Princeton, his name is Richard Gott, he had a theory that said that there's locations near the Earth, sort of between the Earth and the sun, where if you go back 5 billion years before the moon was even there, that material at that time could have collected in these two locations. There's sort of locations where things could sort of hang out relative to the Earth and just stay there. And these are called Lagrange points. And he hypothesized that a bunch of material at 5 billion years ago sort of made its way to one of these Lagrange points and accumulated by more and more stuff going there and made a Mars-sized object. And eventually that Mars-sized object got away from that location and made its way to the Earth and slammed into the Earth to make the moon. So he said, I have my theory that these things could have been formed there, but I have no way to show that they could easily hit the Earth. Like, how could that ever happen? So using this chaos theory I came up with for the Japanese spacecraft, I applied a similar idea to that, seeing how a Mars-like object could ever end up hitting the Earth. And you come up with these very special routes which do this, but it came out of that. And when I went to the computer, a highly accurate computer program to simulate these trajectories, lo and behold, they did actually collide with the Earth with a very high frequency. So with a high enough frequency that we were convinced that, this is probably how the object actually did this. So we got it published in one of the leading journals in astronomy called the Astronomical Journal. And it got on the cover of New Scientist magazine. And not to make a pun, it made quite a splash.
A splat, if you will.
Yeah, that was an exciting result that I wanted to share that because it was my first real astronomy problem I ever worked in. Up to that point, it was always spaceships. So to work with things like the size of Mars moving and hitting into the Earth, that was an exciting thing for me to work on. And that was my first foray, so to speak, into the world of astronomy.
Oh, that's so cool. Congratulations, Ed. And it sounds like you've been doing so many different things in science. And I know it's easy for it to sort of consume your life, particularly if you're balancing this artistic side as well. One thing we always try to encourage our listeners to do, and I'm hoping you can help us here, is to read broadly. So we love giving book recommendations to everybody on the show. So Ed, do you have a favorite book, whether it's one you read recently or long ago, that you can recommend for all of us today?
This goes along with a little bit we're talking about. I was highly inspired by this as a kid. You all know the name Carl Sagan, was a major astronomer, popularized astronomy in the 70s, 80s, 90s. And he wrote a book that really inspired me. It's called Intelligent Life in the Universe. And that really inspired me, Intelligent Life in the Universe.
Well, excellent recommendation. And we will add it to our website for our listeners to find if they are looking for something fabulous to read and for some inspiration themselves. And Ed, we've covered a lot of ground in our conversation today, but one of the things we haven't yet touched on are some of the travel opportunities that scientists get. And I know there are a lot of opportunities to go to conferences, to work with collaborators, and just to see the world through your science. So do you have a particularly memorable place or a favorite place that your science has taken you?
I have traveled all over the world. In fact, science has allowed me to do that more than even the art has. So I have been giving conference talks in Barcelona, Spain was my first one, actually. And then I did many trips to Paris. I never ever dreamed I'd ever go to Paris. And then also I went to Paris independently as an artist as well. So I've been there a number of times. Italy has offered me many opportunities to give great talks on science. They have an active interest in space exploration, and they have big aerospace companies. I've spoken at those companies. Recently, I was very lucky to receive the Humboldt Award from Germany. It was for my work on these low-energy, low-fuel routes to the moon, and got to spend a year in Germany. And I met the president of Germany, Steinmeier. I didn't meet Merkel, who's the prime minister equivalent. And I lived there for a year. It was very exciting. And it was such a treat to be outside of the U.S. for a year. I got good perspective. I've been to Rome many, many times. And one of my passions, like everyone, a lot of other people, is Roman ruins and going through all of that, which was exciting. I've spent a lot of time in Rome, actually. And there was a period there of a couple of years. I got a visiting position as a math science professor at a place in Bogota, Colombia, Sergio Arboleda University. It's a very ritzy university down there in Colombia. And I never envisioned myself ever going to Colombia. And yet I was going down there all the time. I loved it there. It was just fabulous. The best coffee you'd ever want to drink is in Colombia. It makes Starbucks taste like nothing. I mean, it makes European coffee taste like nothing. This is coffee. So that was another set of interesting trips I took. And I've been to China. China's a huge place, as you can imagine. The cities were a little bit too big for me. I didn't like the size of the cities. There were just too many people. And it was you talk about chaos.
Right.
But all over Europe. And I have to say, one of my favorite cities in the world is Berlin. I love Berlin. If you look at the before and after pictures, what it was like after they bombed it out in World War II, and you look at it now, you can't even believe anything ever happened there. It's a very, very exciting city. Paris is just incredible. Rome is amazing. London is a great place. So I've had some great opportunities, conferences, giving invited talks, having visiting professorships or winning awards. They're all opportunities as a scientist to travel around. And if you do get a degree in science, chances are you will be given the opportunity to give talks around the world in different locations. And there's many ways to support that financially. When they usually get invited to give a talk that's, let's say, France, they will provide funding for that. And it's a great opportunity. So I think you're guaranteed, if you want to do it, a very robust travel experience, especially to Europe. Not so much the other ones, but especially Europe.
Phenomenal. Ed, it sounds like you've had some amazing opportunities to see a wide variety of places throughout your career. And I appreciate you sharing some of these moments with us. But I think also in science, you get to work with some phenomenal people. And you've mentioned some of them throughout our interview today. And I think there are some stereotypes out there about what scientists are like in terms of being very critical, being very serious, kind of working by themselves in the lab. And I think research is, of course, very important. But for me, at least, some of the funniest and most creative people that I know are scientists. And I think many of us have experienced these either quirky traditions or just hilarious memories and fun times that you shared with your colleagues. So do you have an example or a story of your own, Ed, of one of these kind of more human moments in science that goes against some of the stereotypes people may have?
As I mentioned, my training was in mathematics. So I really initially got involved in the math community. And most of the stereotypes I think of math are probably true. A lot of the mathematicians tend to be more loner types. You don't need a lot of heavy equipment to do math. You just need a pencil and paper pretty much. So mathematicians are very likely to be sitting by themselves in some room just working on equations. You see a lot of that. However, when I started my professorship at Boston University when I got out of graduate school, and I really expected that I'd be with that kind of person. And instead, what I find out is that these guys at BU, when they hired me in, every single night, they would drift over to the Boston University pub and just drink. I mean, beer, unlimited quantities of beer. So I never had that impression about mathematicians ever. So at least in the BU environment, that was definitely the case. For the most part, I think mathematicians tend to be a little more reserved. However, the scientists are a different story. The ones I've met are very outgoing and real quirky types, just a lot of fun. Typically, the scientists like to travel a lot. They like to go out and do things. They don't like to be sitting inside a little closed office. It's pretty much different from the mathematicians. I don't know really what to describe, except that my experiences when I'm around the science community, like the astrophysics community at Princeton, it's very exciting. The people are very outgoing and want to talk about this, want to talk about that. They're very much up to speed on current events. They're very much aware of what's going on with NASA because NASA funds a lot of their own research. So they're very up on the space program and world travel in general. Now, the math community is sort of like that, but they're not quite as outgoing, but they are world travelers. But the math person, from my experience, tends to be a little bit more closed off in the office doing their own research.
Gotcha. It sounds like the mathematicians, though, that you met at least had that work hard, play hard mentality. They didn't spend all their time there in the lab, which I think is important.
I really enjoyed working with them when I was there.
Oh, I love it. Well, Ed, thank you for helping us break some of the stereotypes out there today. And we touched on some of the amazing projects you're working on. And I think for all scientists, really, things like funding, staff, technology, feasibility, resources, computational resources, whatever it might be, often limit what you're able to answer. So for you, if we took away all of the barriers that normally hold you back, Ed, what is the one question that you are just dying to know the answer to?
How do I win the lottery? Now, that was
unlimited research funding, right?
Yeah. Well, actually, I think the origin of our universe. We're brought up to believe that our universe got here because of something called the Big Bang. So this supposedly happened about 14 billion years ago. There was supposedly nothing. And then there was some gigantic, I'm going to call it an explosion, even though it was not an explosion, but huge, unbelievable amount of energy was released in a trillionth of a second. And boom, the universe literally as less than a trillionth of a second appears. It's called the inflationary universe. That's what we were brought up to believe, that the universe came out of nothing effectively, and here we are. New results are pointing that may not be the case, that it could be a universe that goes on forever, has always been here forever. And we're just one little part of that, thinking that this Big Bang event is the whole thing. It could be just for us. So the universe could be something which just goes on forever. It's always been here. It'll always be here. And we don't really know what the heck is going on. So there's two problems. This is one. Basically, how did our universe get here? What is the universe? Prior to the 20th century, they believed in a steady state universe, that there was this constant creation and destruction of matter that happened all the time, and therefore the universe never changes. That was sort of poo-pooed in the 60s. No, that has to be wrong, and they adopted this Big Bang theory of the inflationary universe. But now we're going back to the other one again, so it'd be really interesting to understand that. And the more current one, which is a science question from my perspective, is there is now unrefutable evidence that there's unidentified flying objects being observed all around our Navy and also all around nuclear storage sites in the United States, to the point where there's going to be a session of Congress on this at the end of the month from the Intelligence Committee, the Defense Committee, where hundreds of pilots have observed hundreds and hundreds of events of these objects moving at fantastically high speeds that can't be anything we've ever developed. And they were called UFOs in the past, and now called unidentified objects. I forget the exact word they're using. But it used to be a topic people would laugh at, but not now. Now it's being taken very seriously because the sightings have gone way up, and they now have 3-point verification. It means that when a pilot sees these, they're being tracked on his radar in the plane, the radar on the boats, Navy boats in the area, and by satellite all at the same time. And they know they're there. We don't know where they're from, what the purpose they have, or anything. And obviously, if they're messing with our nuclear sites, we better know what this is. So the Department of Defense and the intelligence committees for the Congress are going to be meeting on this at the end of the month. I don't think they're going to tell us a lot, but I would love to know what that is.
Well, Ed, I think there are a lot of people who feel the same, and I appreciate you giving me and our listeners some big ideas to ponder today. And I'd love to wrap up our conversation by talking about advice. So if you think back on your own life and your career, is there one piece of advice that somebody gave you that just had a really big impact that you can pay forward to our listeners today?
Yeah, the main, I think, advice to anybody going off into the sciences in particular, because there is a lot to learn, is don't give up.
I think that's so important, Ed. Thank you for sharing it with our listeners today and encouraging them on their own journeys. If our listeners are intrigued and they want to learn more about you and the wonderful work that you do, what is the best way for them to do so?
They can reach me by email. The easiest one to reach me, actually, is not my academic one, but rather my Gmail account, because everybody knows Gmail, right? So it would be edbelbruno@gmail.com. So it's ED, B as in boy, EL, B as in boy, RUNO. So it's edbelbruno@gmail.com. Please contact me. I'd love to hear from you.
Wonderful. Well, listeners, definitely get in touch if you have any questions for Ed. Ed, it has been such a pleasure to chat with you again. Thank you so much for being on the show.
Thank you for me. It was a huge thrill.
Well, delightful to have you here with us. Listeners, great to have you here as well. We'll see you next time on another episode of People Behind the Science.